Welcome to The Explainer. Today, we're going to talk about a really big shift that's happening in the world of systems programming. We're looking at why massive, long-running C++ projects are starting to bring Rust into the mix to tackle some really tough, decades-old problems with security and, just getting work done.
Okay, let's just dive right into this, because if you're a C++ developer, this is a totally fair question. I mean, you've got a whole arsenal of tools at your disposal to write safe code. The answer, though, it isn't really in one specific tool, but it's hidden in decades of data from across the entire industry.
You see, for years, there's been this one single, really stubborn number that's kind of haunted systems programming. It represents this huge, expensive challenge that companies from Microsoft to Google have been wrestling with for a very long time.
And that number, it's 70%. Think about that. Across the board, something like 70% of all high-severity security bugs come back to one single root cause: memory safety. And this isn't a fluke, it's a pattern that we see repeated year after year after year.
This is not a new problem at all. In fact, it's the foundation for some of the biggest, most infamous security disasters in history. We're talking about everything from the slammer worm that brought down networks to the Heartbleed bug that left countless servers totally exposed.
And this isn't just ancient history. Even today, in one of the biggest, most well-maintained C++ projects on the planet, Chromium, these kinds of bugs are a constant daily fight. It's just a never-ending stream of use after freeze, out-of-bounds access, buffer overflows, you name it, all needing to be found and patched. So, how has the C++ community been dealing with this? Well, with some incredible creativity, actually. The effort has been nothing short of heroic, but it's also kind of shown the limits of just trying to mitigate problems after the fact. It's like being on a treadmill that just keeps getting faster.
I mean, the list of fixes and workarounds is huge. We have architectural patterns like sandboxing anything risky. We've got incredibly advanced tools like fuzzing and static analysis. The C++ language itself and its libraries have been hardened with all sorts of runtime checks. And of course, there's nonstop developer training. It's a full-on effort.
But here's the thing. Even the best strategies have their downsides. Take sandboxing. It's a pillar of browser security, right? But isolating everything takes a toll. It uses up a lot of memory, it can slow down performance, and that really affects the health of a device, especially if it's not a high-end machine.
And what happens when we do find a bug? Well, that's where it gets really interesting. This workflow here shows that just spotting the issue, that's only step one. Every single step after that, a senior engineer has to analyze it, document it, code a fix, roll it out globally. It all takes a ton of manual effort. And that is a huge drain on productivity.
And this isn't just some theoretical cost. The real-world result is a backlog of over 2,500 known dangling pointer bugs in Chromium, just sitting there, waiting to be fixed. It's the perfect proof that just detecting bugs at a massive scale is a totally different problem than actually fixing them at scale. That mitigation treadmill just keeps on spinning.
So this whole endless cycle of finding and fixing, it's led the industry to ask a really different kind of question. Instead of getting better and better at catching our mistakes, what if we could make it impossible to write those mistakes in the first place?
And this really just captures that whole paradigm shift perfectly. Mitigation is reactive. You're hunting for bugs after they've already been written. Prevention, on the other hand, is proactive. The whole goal is to make entire categories of bugs impossible to even compile. It shifts the burden of remembering all these complex safety rules from the developer to the compiler itself.
Let's look at a super classic C++ problem. I'm pretty sure every C++ developer has hit this. You've got a vector, you grab a pointer to an element, and then you add something new to the vector. If that causes the vector to resize, well, your original pointer is now dangling. It's pointing to garbage. Classic use after free bug waiting to happen.
Okay, so now what happens if you try to write that exact same piece of logic in Rust? Well, it just won't compile. The compiler has this thing called the borrow checker, and it has very strict rules about who owns what data. It knows that pushing to the vector requires changing it, but you still have this other pointer that's just looking at it. The compiler sees this as a potential conflict, a classic memory bug, and it stops it right there at compile time.
And that quote just nails the core idea. Safety is no longer just a suggestion, a best practice that a developer has to remember perfectly every single time. It becomes a hard and fast rule that's enforced by the compiler, by its very design.
Now, this all sounds fantastic in theory, right? But does it actually work when the rubber meets the road? Let's check out the data from some of the biggest software projects in the world.
So let's start with Android, which is just a massive code base. If we look at the new code being added, the trend is, well, it's pretty obvious. The amount of new C++ is heading down. while the new Rust code is growing, and growing fast. This isn't just a little experiment. It's a real strategic change in how they're building critical new parts of the system.
So what's the actual impact of that change? It's pretty staggering, honestly. We're talking about a 1,000 times reduction in the density of memory safety bugs in Android's Rust code compared to their C and C++ code. Just let that sink in. Not 10% better, not 50% better, 1,000 times fewer of these critical bugs. This is the prevention model just flexing its muscles at an incredible scale.
And what's really cool is this isn't only about security. It's about productivity too. Google's internal data tells a really clear story. Rust teams are more than twice as productive as similar C++ teams. A huge majority, 85%, say they're more confident their Rust code is actually correct. That confidence means things move faster. Code reviews take about 25% less time. And the ultimate proof? Services built with Rust are rolled back 4 times less often. The code isn't just safer, it's just plain more robust.
So, what does this all mean for the future? Well, it's definitely not about throwing away decades of C++. It's about being smart and augmenting it for a safer path forward.
The strategy is actually pretty simple. It's called closing the tap. All the research shows that the buggiest, most vulnerable code in any project is the new code you're writing today. So the idea is to use Rust for new stuff, especially high-risk things, to stop introducing new memory bugs at the source. Meanwhile, the giant, battle-tested C++ codebase keeps on running everything else.
And that, at the end of the day, is why Rust gets the call. It delivers this amazing trifecta. You get that memory safety baked in by default. You actually get better performance because you can get rid of some of that heavy mitigation overhead. And developers are just more efficient and confident. It's all in one package.
Which leaves us with one final big question to think about. As our software systems get more and more complex, is this shift away from relying on perfect human discipline and instead towards safety that's enforced by the language itself? Is that just an option, or is it an absolute inevitability for the future?